Thank you. And thanks for the opportunity to speak here. I couldn't think of a more appropriate place really to elaborate on this theme, so thank you. So I'd like to offer some reflections on our understanding of our place in the universe that have emerged from a fundamental paradigm shift that's been unfolding in theoretical cosmology. And it concerns the epistemic root of our theory of the Big Bang and of the earliest stages of the universe. Of course, the idea of a Big Bang goes back to the work of Georges Lemaitre. What you see here are the very first graphs, I believe, ever drawn of an expanding universe or of evolving universe. And all the way at the bottom left, barely visible, you see t equals 0, the zero of time, what we now know as the Big Bang. Now, the point I want to make here is that even back then, Lemaitre realized that most of these universes are not habitable. In fact, he selected just one, which he thought would be habitable, evidently the one going off horizontally, thinking that you would need a long phase of very slow expansion in order to form galaxies and eventually life. Since, and he called this a hesitating universe. Now, since those early days, the strange biophilic character of our universe has, of course, become even more baffling. It manifests itself today at all levels. The composition of the universe, of course, as you know, but also the ratio of the particle forces, and even the simple fact that we have 3 dimensions of space and 1 dimension of time. So, as Fred Hoyle would say, the universe looks like a fix. And so that's interesting, right? Because while at first sight, it would seem like an extravagantly long arc from the Big Bang or the first galaxies to our human conditions here on Earth, that observation, the observation that there's something strangely biophilic about the laws of physics on which the universe runs, suggests there is really something to be understood. So what should we make of it? How does our existence tie in with our cosmological theory? That's the question I'd like to elaborate on for a few minutes. Now, various explanations over the years have been put forward, none of them particularly convincing. Some would say it's not science. Others would say, well, it's a mathematical necessity. That's the grand old idea of a final theory, an idea born with Einstein, adopted by the earlier Hawking, and so forth. But yet others would say, well, maybe we live in a multiverse. Maybe there are many universes, most of them lifeless. Once in a while, you'll find a good one with the right mixture of ingredients. And so I've looked into this question for many years with collaboration with Stephen Hawking, and rather foundational doubts about the multiverse as a scientific paradigm led us to question some of our basic assumptions behind cosmology. And one day, Stephen put it like this to me. As you will see, Stephen is gonna offer a mea culpa, and he's then gonna point to something that has been at the very roots of physics and cosmology for centuries, really. In fact, since this academy was established. And that's the simple fact that in physics and cosmology, we've become experts at looking at the systems which we want to study as if we are outside. And normally that's okay, of course. James Webb looks at distant galaxies, distant stars, and so forth.
A brief history of time is written from the wrong perspective. We are not angels who view the universe from the outside.
Of course, in cosmology, we all know that it's fundamentally wrong. Yet we have practiced cosmology as if we're outside. In fact, this idea of a multiverse is sort of an extreme version of it. We've put ourselves with that paradigm outside the universe and looked at the whole. And most of the time, even cosmology get away with this, except when you're so crazy as to ask this one question: why is the universe biophilic? What is the relation between our existence and the universe? At that point, of course, it's obviously wrong to put yourself outside of this game. So in a sense, my entire program with Hawking for many, many years was to sort of try to get away, to let go of that Archimedean viewpoint and to turn cosmology inside out. Now, how do you do this? Well, in fact, something was sort of waiting for us. The roots of quantum theory, at least the modern formulation of quantum theory, do allow you to do that, do allow you to place the observer, the act of observation inside the universe. That's an idea that goes back to Wheeler. Here he is, who drew a very famous picture. The grand U stands for the universe. Top right, you have the Big Bang. The universe grows and evolves. But then there's this I on the top left corner and that dotted line to indicate that the past, our past, in quantum cosmology, is a wave function, is a superposition of histories, which the quantum act of observations selects one or the other. And while in Wheeler's day, this idea was far-fetched and sort of an idea for an idea, as he called it, strikingly, that concept ended up at the center of the models of the Big Bang that Hawking and I would develop. How come? Well, it has all to do with the way that gravity and quantum theory talk to one another. You've heard that quantum theory and gravity are at odds with each other, but in the last 15, 20 years, theoretical physicists have understood how these two really can live together. And the surprise has been that quantum theory and gravity relate to one another in a holographic manner. The gravitational systems have holographic properties, meaning that one of the familiar dimensions is in fact an emergent dimension. And which dimension? Well, it turns out that the time dimension, the one which was problematic since Lemaitre's days, is in fact viewed in quantum gravity as an emergent property of the universe. So think of a black hole. A quantum description of a black hole would be some sort of hologram located on the horizon of the black hole, and the interior of the black hole, which is a time dimension, would be an emergent property. So how do you apply these ideas to the entire universe? This is a very pictorial schematic illustration of this. The Big Bang is in the middle, the universe expands towards the outside, and all that evolution in quantum gravity would be captured in terms of a hologram for which this history is emergent. Now, of course, in the usual circumstances, this is completely not needed. But when it comes, with the usual picture of our reality breaks down, near black holes or at the Big Bang, then that holographic thinking becomes crucially important, because that's where our four space-time dimensions picture loses meaning. And so here, for instance, you might wonder, well, how do you go back in time? How do you go from that hologram, which is a sort of abstract representation of the present state of the universe? How do you go back in time? Where is this extra dimension encoded? It is encoded, of course, in a very strong quantum entanglement between these different qubits that make up the hologram. So how would this look in normal space-time language, going all the way back to the Big Bang? Well, if you were to do this in Einstein's theory, going back all the way to the Big Bang, you would hit a singularity, you would hit a zero of time. If you go back in this quantum thinking, something else happens. The time dimension and the space dimension merge. Time becomes more and more fuzzy, merges with space, and that offers a new possibility for the Big Bang, namely, the past gets rounded off, as you can see on the picture. And that avoids, of course, the question which was alluded to earlier: what would be the nothing before the Big Bang, well, the nothing would here be clearly outside the theory and play no role. This, in fact, what you see there, the merging of time and space, is sort of the culmination of a process of unification which happened in the earliest stages of evolution of our cosmos. You can look at the first fraction of a second of the evolution of the cosmos in this way. Top, we have the forces we have today. We go back to the Big Bang, and the distinction between the various forces, the various particles, gradually disappears. That's what we know as the particle physics program unification. Now, we've always thought that we would hit a fundamental layer, a unified theory, an immutable set of laws transcending the universe, transcending the physical universe. The crux of the theory of the Big Bang that I developed with Hawking is that was a mistake. That in fact, this process of unification, simplification, goes on all the way. And that the origin of time, Lemaitre's zero of time, is in fact also the birth of physics itself. The laws of physics themselves seem to disappear when you go back to the Big Bang. How is that translated in that weird holographic language? Well, in a holographic cosmology, you go back to the past by losing more and more information encoded in your hologram, by taking a coarser-grained view of that hologram. And eventually, of course, you run out of bits, you run out of data. So it's the Big Bang, from a holographic perspective, becomes an epistemic horizon. So this is what we used to do. Come up with a physical theory, an immutable set of laws, derive what physical universe comes out, and observe it. That's the model, the ontological model behind cosmology that was forcefully put forward in Hawking's earlier work. This is how we would do it now, how the later Hawking thought about it, much more constructing a physical theory rooted in our observational situation and the universe. In fact, you see that James Webb is not completely absent there, right? So in a way, I think, looking back on our work, I think we try to crack open physics. You know, normally physics is about evolution. It's about dynamical law. And stuff about boundary conditions or observership or questions we ask is not considered part of the law. But I think when you really push these laws to the extreme, we are encouraged to broaden our view of what physics is about. And this is a new ontological scheme of physics, which sort of encapsulates its own origin, its own limitation, I would say. And in fact, strikingly, that kind of conception of physics has been sort of anticipated by none other than Hannah Arendt. So in 1958, she wrote a book called The Human Condition, in which she reflects on the loss of a sense of belonging. And she remarkably traces the roots of what she called world alienation to the central insight that sparked the modern scientific revolution, namely the idea that the world is objective, governed by higher truth in the form of rational, immutable universe law. Now, she, of course, argued that this is going to be a self-defeating paradigm. And she writes that man will necessarily lose his advantage. We can only get lost, for the only true Archimedean point would be the absolute void behind the universe. Well, I feel that the vision we laid out is a response to her concern. By abandoning an Archimedean standpoint on the cosmos, one can hope, I think, to plant the seeds of a new worldview in which the knowledge we gather and the creativity we treasure will once again revolve around their common